What are the topics in the subject? If you talk about the topics, this is physical quantities. First is physical quantities and units, correct? So this is the topic for AS level physics. Okay. And then second topic is what? Your kinematics. Then third topic is dynamics. Okay. And then we have forces, correct? Forces, then density and pressure. Okay. And then what you have next is work energy power. Okay. Work energy power. Sixth one is deformation of solids. Correct. Deformation of solids. And then you have waves. And then you have superposition. Correct. Then the next topic is electricity. And the next topic is DC circuits. Particle physics, correct? Particle physics. Correct. So these are the topics that you have in this unit, okay, for AS level. So if you talk about this, if you talk about the physical quantities of any given physical quantity. So if you talk about any physical quantity, it's basically once you are defining, let's say, mass. Okay, mass is defined in kgs, correct? So its unit is kg. Its dimension is what? Dimension is m, correct? Similarly, if you talk about, let's say, length. So what is length? So length is defined in L, correct? And unit is meters, correct? Similarly, you have time. So time is defined in T and it is defined in seconds, correct? And then you have got electric current, correct? Electric current. Electric current is in amperes, correct? So it is in amperes. And you basically denote it by A. Okay, and this is amperes, correct? Similarly, you have got next one. Which one? That is temperature, correct? Temperature is defined in kelvins, and this is Kelvin, correct? And then what you have? Then you have got luminous intensity, correct? Luminous intensity. So luminous intensity is defined in what? Candela, correct? CD, isn't it? So this is candela. And then next unit is amount of substance, correct? Amount of substance. Amount of substance. You know this? Amount of substance is given in moles, isn't it? So these are your 7 basic fundamental units. Okay, you can remember it with a acronym, that is LM TETLA, correct? That is length, mass, time, electric current, temperature, luminous intensity, ampere is the current. Okay, so if you have any of the derived unit, like say Newton, okay, force, if you talk about force is given in newtons, correct? Similarly, pressure is given in pascals. So these are derived units. Okay, these are derived units. Okay, and you can define the dimensional formula for force, pressure, and derived units. Like for force, basically force is defined as mass times acceleration. So I know that mass is given in m and acceleration is given in meter per second square. So it is L T minus 2. This basically given as ml T minus 2. Correct? Similarly, if you talk about pressure is force per unit area. So if I talk about force per unit area, force is given by mlt minus 2 and acceleration is given by lt minus 2. Sorry, force per unit area. So this is L square and this one would be ml minus 1 t minus 2. Correct? ml minus 1 t minus 2. Understanding this part? So pressure is given as L minus 1 t minus 2. Getting this? So you can derive the units for the various physical quantities. Okay. Then we read in the topics that if you have, let's say, any equation, let's say x is equals to ab plus y. Okay. Then all of these terms must have the same units. Same units. Okay. Same units. For example, if I write equation, let's say v is equals to u plus at. Okay. So v is given in meters per second, u is also given in meters per second, and this whole term must also have meters per second. So I know that acceleration is given in meters per second square and time is given in seconds. So I will get what? At. And at is what? In meters per second only, isn't it? So all of these terms, v, u and at must be in meters per second. Correct? So the demonstration validity is obtained over here. Similarly, if you talk about, let's say, e to the power something, okay, e to the power minus at, then this term must have no dimension, okay, no unit. For example, if I'm writing like e to the power at, then t is given as what? Seconds, correct? So if a has to be defined, then time is given, the time is seconds. So this one would be a is equals to 1 over second, correct? So this is a given as second minus 1. Or that. So remember that the dimensional validity of an equation must hold true. Then only we can solve for the physical quantities. Okay. Is, if you talk about the next thing, that is the next thing is basically your dimensional analysis. Okay. Dimensional analysis. We use the dimensional analysis to find out unknown formulas. For example, if I want to calculate, let's say, time period. So time period is given by 2 pi under root L by G, correct? So we know that time period can be derived on the basis of L and G. So I know that there is some power of L, some power of G, correct? Now I know that from the left hand side, what is the dimension? So if I get this, so this is time to the power 1, okay? And from the right hand side, if I talk about, then L is having the power of A, isn't it? And G is given as what? Meters per second square, correct? So this is to the power B. So what I should write? I will write L to the power B and then T to the power minus 2B, correct? So if you add both of them, because this is time is directly proportional to length to the power A into G to the power B, that is length to the power B into T to the power minus 2B. What I will get? I will get time period is directly proportional to length to the power A plus B and time to the power minus 2B. Getting this? And this is 1. So now we'll compare both of them. I will get A plus B is equal to 0 and minus 2B is equals to 1. So I will get B is equals to minus 1 by 2 and A is equals to 1 over 2. Correct? So I can now write time period is equals to 2 pi under root L by G. Although I will not be able to identify the constants, but I will be able to find out the relationship between the various parameters in order to obtain this result. Okay, that is the time period. Correct? So this is the part for the dimensional analysis. There are one more thing that is known as uncertainty. Okay, uncertainty we also define, and we define 3 types of errors. We have got 3 types of errors. One is known as the absolute error, one is known as the relative error, and third one is known as the percentage error. Correct? So how we define the absolute error? Absolute error is basically defined by, let's say, you have got the true value and you have got the measured value. So my measured value minus the true value, and you take the absolute value of that. Basically, if it is a negative value, it will become positive. If it's a positive value, then it will be positive. Correct?
Okay.
If you talk about relative error, how do you define the relative error? You basically find out the change in the this is your delta x. Okay, you take delta x, and then what you do is delta x over x is your relative error. Okay, sometimes also known as the fractional. And the third thing is, if you want to take percentage delta x over x into 100, you have to do for making it a percentage error. Correct?
Yeah. Correct.
Sometimes the problem comes like this. Suppose there is a quantity given, let's say a equals to x to the power a, y to the power b, and z to the power c. And I want to find out the error percentage in a. Okay. So how I will define that? So what I will do is I will take delta a over a is equals to how much? A times of delta x over x plus b times of delta y over y plus c into delta z. Okay, over there. Here,
okay.
This is your
yes.
This is the concept for the error calculation in a quantity. Okay, so these are the topics that you should know in the physical quantity and units. Got that?
Yeah.
Clear with this part? So now I will go to the next chapter. What is the next chapter?
Can I also take a picture?
Okay, I will send it. Okay.
Okay.
I've already taken. Next one is kinematics. Now, if you talk about kinematics, you have got various terms. Okay. First term is basically your position. When your position changes, then what happens? The distance is covered. Correct? Or displacement. Correct? And if you talk about the speed, then this speed is given by distance over time, or you define the velocity. Okay. And then what we define is when the velocity changes, then you have an acceleration, and this acceleration is given by change in velocity by time taken. Correct? And then these are the quantities which are independent of the force. So we talk about independent of force and then solve for all of them. Correct? Now, if you talk about the position, so position is defined in x. When you have a change in the position, then you basically get the displacement. Okay, so it is the shortest path.
Okay.
You remember that shortest path from initial to final position, and this distance is given by what? That is the path length covered. Correct? Path length covered. Whatever the path length is covered divided by the time taken, that path length divided by time is what? That is your speed. And similarly, if your velocity is known, so velocity is displacement over time taken. Okay.
Yeah.
And then you have acceleration. If you talk about acceleration, acceleration is just change in velocity by time taken. Okay. So we have got this position you define with respect to some reference point, isn't it? So you define with respect to reference point and you call it the position. If you talk about the distance, you have to, it is always positive. Distance is always positive. Always positive. And it will never going to decrease. Even though the particle comes back to the original point or the initial position, then also the distance will keep on increasing while the displacement becomes zero in that case. Correct? It can be negative, positive, or zero. Negative, positive, or zero. Clear? If you talk about average speed, average speed is always remembering that is total distance over total time taken. Isn't it? Total distance over total time taken. If you talk about average velocity, what is average velocity? Average velocity is total displacement over total time taken. Getting this?
Okay.
And if you talk about acceleration, acceleration is change in velocity by change in time taken. Now you have two types of quantity, that is vectors and scalars. if you talk about vectors and scalars are those quantities which require only magnitude, while if you talk about vectors need magnitude and direction both. Okay.
Okay.
So this is the basics of the vectors and the scalars. Now, if you talk about the displacement, it's a vector, velocity is a vector, acceleration is a vector, while distance and speed is the scalar quantities. Okay.
Yeah.
You've got some graphs as well. So if you talk about the graphs, we can have graphs based on position time. So if you talk about position versus time graph, okay, position versus time curve. Then on a position versus time curve, if you take any slope, it will give you what? It will give you on a position versus time curve. What it will give? It will give you the speed at this point, instantaneous speed or velocity at that point. Correct?
Okay.
But if you talk about the velocity versus time curve, okay, VT curve, then if you take a slope on that curve, it will give you acceleration at that point. Okay, that will give you the acceleration. And if you talk about the area under the curve, okay, with the sign, suppose signs are included. Suppose the curve goes like this and goes down. And if the sign is taken, okay, plus minus. So when the sign is taken, then it is called as displacement. Correct? If the sign sign taken, displacement. If the sign not taken, it's a distance. Okay, sign not taken.
Yeah.
Understood this part?
Understood.
And if you talk about acceleration versus time curve, okay, and you take the slope of that curve, it will give you what? It will give you jerk. Okay, and if you take the area under the curve, that area will give you the change in velocity. Okay, so that is change in velocity. Okay, so that will give you change in velocity, means final velocity minus initial velocity. Okay. Final minus initial velocity. Got that? So this is the part for the velocity part. Okay, the next thing is basically your kinematic equations. Okay, kinematic equations. If you talk about kinematic equations, you have got certain equations. What are the equations? We have got V is equals to U plus AT, S is equals to S, or you can say delta X is equals to UT plus half AT square. Okay, and third equation is V square is equals to U square plus 2AS, and the displacement in the nth second is equals to U plus A by 2 into 2n minus 1. Okay, so if you talk about this, so this is your kinematic equations. This is for the displacement in the nth seconds. Okay, displacement in the nth second. But all these equations hold true only when acceleration is constant in direction, in magnitude, like the case of the falling ball, or let's say projecting a ball upwards and then going backwards. Okay, so this is your kinematic equation. Understood this part?
Yeah, understood.
So majority of the problems are based on the kinematic equations and these basics and the graphs. Okay. Okay. We'll go to the next part. That is your dynamics.
Yeah.
I've not taken the screenshot. Okay, I'll take it from the video. Okay. Next.
Okay.
You have got dynamics. Dynamics is basically what? Dynamics is the force analysis. Okay. Force analysis.
Okay.
You've got three laws in that. What are the first law? First law is the law of inertia. That is the law of inertia. Correct? And this basically defines the mass. So if the mass of the body is high, the acceleration would be less. If the mass is less, then the acceleration would be high. Okay, depending upon the force. Then the second law is there. Second law is that is the force law. That is force is equals to mass times acceleration or in the body. Okay, so if there is any mass in the body and then it can accelerate, then it will be due to the force that is acting upon it. So if the net acceleration has to be found, then it is given by F by m. So if the mass is high, acceleration would be less, and if the mass is less, acceleration would be high. Okay. And if the net force on the system is equal to 0, then it is called as equilibrium. Okay. In equilibrium, you can have net force in the x direction must be equal to 0, then the net force in the y direction must be equal to 0, and similarly in the net force in the y direction must be equal to 0. Sorry, z direction must be equal to 0 in order to make the equilibrium condition. Okay. And in that case, what happens? In the equilibrium case, the velocity can be constant, or there can be the position of rest condition. Rest condition means the net velocity is 0, so the particle is not moving. Then we have got the third. What is the third law? Third law states that if you talk about the net force, okay, on a body, then it also includes the internal forces. Suppose there is a body like A, there is a body like B. Okay. So now what happens? If they are in contact, suppose I apply a force F1 over here, what will happen? A will apply the force on B towards rightward direction, correct? So it will be acting like this.
Correct.
The force on B due to A, and similarly force on A due to B would be leftward. Getting there? And this would be equal and opposite in nature, and they act on different bodies. Remember that they act on different bodies. Okay. Next thing is there are action and reaction forces. Okay. Action and reaction forces. And they are always equal and opposite to each other. Equal and opposite to each other. Clear with this part?
Yeah, clear.
So this is the part for the third law. So majorly in this part, forces, they have covered the problems only. Okay, you can look over the videos to understand how the problem is solved. Okay, we have got next concept of friction as well. So we have a friction. So there are two types of friction basically. One is known as the static friction, and another is known as the kinetic friction. And remember that the maximum value of the friction, that is the static friction, is higher. That is the limit of friction is higher, that is equals to mu Sn, and that is very high in comparison to the kinetic friction, which is lower. So that Fk is mu k into N. Okay. So this is your maximum friction. But Fs is a variable quantity and it can vary from 0 to mu Sn. While this is constant, this kinetic friction is constant. To know that there is a graph that is followed for the friction. So it is basically like this. Okay. So this is the maximum value of friction, that is mu Sn, and this is mu k. Okay. And you can see here, this is your friction, and this value is applied force. Okay. So as the applied force increases, what happens? The friction force also increases up to this maximum value, and this is your normal force. So suppose there is a body like this, m mass body, mg weight, normal force. F you are applying from the left hand side, the friction will act opposite. So this friction will increase up to mu Sn and then decrease to mu Kn, and then it will be constant in nature. So this is the static and kinetic friction. Okay. So up to certain limit, the static friction increases, and at some time it stops, and then what happens? Kinetic friction acts, which is lower in value. Okay. So this is the part of the static and kinetic friction, and even you can have problems based on block placed on another block, or the blocks tied to the strings, and then you solve for the frictions. Okay. So these problems you can watch for the from the other videos. Okay. The third chapter. Now if you talk about the next chapter, that is what? Forces, density and pressure. Okay. Forces, density and pressure. So basically we have already talked about forces. Now we'll talk about density, pressure. Okay. So basically, if you talk about density, density is given by mass per unit volume, mass of the body divided by volume of that body, and that is given by kgs per meter cube. Okay, so this is given in kg per meter cube or gram per centimeter cube. In this, you should remember that the water is having the density of 1000 kg per meter cube. That is given as 1000 kg per meter cube, or it's 1 gram per centimeter cube. Okay. And density of water is maximum at 4 degrees Celsius. It is maximum at 4 degrees Celsius, and its density is like this. You can see over here. At 4 degrees Celsius, the density is maximum. Okay. Beyond that, if you talk about that, so this density is lower. So this is a specific volume. Okay, this is a specific volume, that is 1 over density. Okay. So specific volume is inversely proportional. So you can see over here. So it is minimum at 4 degrees Celsius. Okay. So remember that density for the solids is always higher than the liquids than for the gases. This is the order that it follows. So this is the density part. Okay. Now, if you talk about the pressure, pressure is basically defined as whatever force you are applying per unit area, and that is given as a Newton per meter square. So this is given in Newton, this is meter square, so it will be Newton per meter square. Correct? Newton per meter square. This is your pressure. So if you are, let's say, putting a pencil over here, the force is very high, the area is very less, so the pressure would be very high. That's why it goes inside the paper or whatever the cloth is there. Okay. So this is basically your pressure. So if you talk about the pressure in liquids, that's more important. So pressure in liquids. If you talk about liquids, basically what happens, the pressure is higher towards the bottom and lower towards the up. So if you see that this pressure is lower, okay, so P1 is lower and P2 is higher. So if I talk about it, let's say the depth is h and the density of the liquid is rho, I can say that P2 is equals to P1 plus rho GH. Okay, so this pressure difference is there, and due to this as well, the buoyant force acts. So this buoyant force will act in the upward direction, and this buoyant force is given by FB is equals to rho into whatever the cross-sectional area into height. Okay, rho AH into G. So that buoyant force is given by whatever the volume of the liquid displays, whatever the weight of that liquid is, that force will act in the upward direction. This only acts because of the pressure difference. Clear?
Yeah, clear.
This is the weight of the liquid displaced. Okay. And remember that density of mercury is always higher than density of water, that is given as 13.6 gram per centimeter cube. So this is the part for the pressure in the liquids. Okay. Now if you talk about so you and also remember pressure at the same levels is same, that is given by Pascal's law, and the same level is same, that is known as Pascal's law. Okay, so this is Pascal's law. This is the part with this. Now the next topic is over here, density is done, pressure is done. Okay, so these are the topics, I think. The density and pressure. Okay, one more thing is also there, that is your stress and strain. Okay, stress and strain. So if you talk about stress is a internal resistive force developed per unit area. Okay, so internal resistive force per unit area, that will give you the stress. Understood this part? So this is given as sigma. and then you have got a change in length. Suppose you apply some force, then what happens? The change in length is there, so it will be this length, new length. Okay.
Okay.
So what will happen? This is your final length, that is given as L naught plus delta L. Okay. And whatever the change in the
Okay.
length they are divided by original length, that is given as strain. So strain is given by change in length divided by original length. And if you talk about the strain energy, then the strain energy is given by area under the force versus versus extension curve. Okay. And then
Okay.
if you also want to take the area, then area under the stress strain curve will also be given by this. Okay, stress strain curve.
Okay.
And this area is given as 1 by 2 stress into strain, because you know that it follows Hooke's law, and Hooke's law basically gives a linear relationship between the stress and the strain, and up to certain limit only this is followed. So if you talk about area, so area is 1 over 2 stress into strain into, you have to calculate the volume as well, volume of the body, that will give you the stress. Okay, so this is the part for the stress strain, and you have the constant of proportionality, that is known as the Young's modulus. So Young's modulus is also there. Okay, so Young's modulus is Y, that is given by stress over strain. Okay, so these are the major important relationships in the stress strain energy, and the density pressure concept. Clear?
Clear.
Now, if you talk about the next concept, what is the next concept? That is work energy power. Okay, that is your work energy power. If you talk about work energy and power, so you have got three concepts, correct? So what we do is work energy and power. We have got three concepts, that is work, energy, and power. Basically, whatever the work is done on a body, that is given by force times the displacement times the angle. Okay, cos of angle between them. So I will calculate the work done as force times displacement times cos of angle between them, that is cos theta. So work done is over here in given in Newton meter, and cos theta, theta is the angle. So this is the work done in Newton meter, that is given in joules. Okay, and it's a scalar quantity. And there are some important theorems based on it. First is your work energy theorem. Work energy theorem says if you do some work on a substance, on a system, then the net work done by all the forces is equals to change in the kinetic energy of the substance. Okay, and kinetic energy is given by half mv square. Okay, for a particle of mass m moving with a speed v. So this is your kinetic energy.
Okay.
One more thing, if you talk about forces, there can be conservative forces where the energy is conserved, like gravitational forces. Okay, so conservation forces basically are having gravitational force, spring force. Okay, so these are conservative forces. But if you talk about non-conservative forces are those which incurs a loss in energy. Okay, like friction. Okay, and work done is part dependent, so it's basically produced into heat, and heat cannot be utilized in such a case. Okay, so work energy theorem is based on that, and from work energy theorem only, for the conservative forces we define the conservation of energy. Conservation of energy is defined as sum total of potential energy plus kinetic energy is constant, that is your total mechanical energy is constant. Clear? And that is given as, and this is given as, so if you, let's say there is a mass, okay, and you define, let's say, h height, then the potential energy is mgh. Okay, u is given as mgh, kinetic energy is given by half mv square at certain point. Okay, that is given by half. And
Okay.
so this is your kinetic energy. Clear? So this is the part
Correct. Clear.
that you should know. Okay, next part is basically if you talk about the spring forces. So spring force again is a Hooke's law based force which states that whatever is the extension, depending upon the extension in that spring, okay, this is your natural length. Suppose you apply some force, this is having some spring constant. Suppose you elongate it by x, then what happens? The spring force will act in the backward direction, that is given as kx. Okay, and the energy is stored. So this is the spring force, and the energy stored in the spring is given as half kx square. And if you talk about the total of this concept, so basically if you draw the x versus f, that is linear case. Okay, so this is f is equals to kx, that is followed in springs. Clear? So this is the part for work and energy. Now if you talk about what is your power, power is defined as the rate of doing work. Okay, rate of doing work, and this is given as what? Rate of doing work is given as work per unit time. So whatever is the work done, dw by dt, or the average power if you want to calculate work done during the whole interval divided by the time taken. Clear? So that is
okay.
Power.
Clear.
So these are the major concepts in work energy theorem. Okay. Okay. In the deformation of the solids, first topic is deformation of the solids. First topic is your stress that we just now found, that is force per unit area. It's a normal stress, correct? Then you have got strain. Strain is your elongation divided by, so that is change in length divided by original length. So this is your elongation. Okay, elongation per unit original length. Got it then? And then I discussed about the energy. So energy is stored in the stress strain curve. Okay, so basically when a body is strained, it is having some strain energy stored, that is given by 1/2 stress into strain into volume. Okay, or area under the curve. Okay, now we'll discuss about of fx. Okay, where x is the elongation. Similarly, if you talk about the shear stress, okay, there is a one more term that is given as shear stress. Shear stress is given by, suppose there is a body and you apply some force parallel to that surface. Okay, then what happens? There is elongation in this part. So basically this got tilted. Okay, so theta is given. So in this theta is your strain. Okay, that is your shear strain. Theta is your shear strain, and basically your tau is the shear stress. Okay, shear stress. And this shear stress is given by tau is equals to force which you are applying divided by tangential area. So this is your tangential area. Okay, tangential area. So this force by tangential area is given as the shear stress, and theta is your shear strain. Okay, theta is your shear strain. Now if you talk about what is your modulus of rigidity, so this is a ratio between shear stress and shear strain. So this is tau over theta. Getting this? Tau over theta. So this is your shear stress and theta is your shear strain. Okay, and this is divided by g. Okay, and there is one more term that is known as modulus, Young's modulus of elasticity, that is E. E is equals to 2g into 1 plus mu for homogeneous substances, where mu is your Poisson's ratio. I will discuss about the Poisson's ratio as well. So this is your Poisson's ratio, and it is also given as E is equals to 3k1 minus 2 mu, where if you talk about k is your bulk modulus of elasticity. Okay, bulk modulus of elasticity. There is this term that is known as the This is your Young's modulus. This is already known to us, Young's modulus of elasticity. And one more term is there, that is mu, Poisson's ratio. So this Poisson's ratio is given as what? Poisson's ratio is given as, that is given as mu, and this is basically equal to lateral strain divided by the longitudinal strain. Okay, lateral strain divided by the longitudinal strain. So what is lateral strain? So suppose there is a body like this, suppose there is a body like this. So what will happen as it elongates, this will be your final length. So what will happen, there will be some change in the length, correct? So this change in the length divided by the original length, okay, delta L plus L initial would be this final length. So if I talk about whatever is the elongation in the longitudinal side divided by the, so that is basically your longitudinal strain, and lateral strain is your this compression in this side. Okay, so diameter will decrease. So I will write delta D minus delta D over D divided by delta L over L. This is your Poisson's ratio. Okay, so this is your diameter. So this is the terms, and you can use these relations for homogeneous and isotropic bodies. Homogeneous means same type of particles, okay, similar type of particles, and isotropic means in all the directions the system will behave in the similar manner. Okay, the properties will be in the similar manner, correct? So this is the part for the deformation of the solids. Okay. Solved some problems based on this as well. You can also go through them. Okay. Then we have next topic, that is waves. Okay, waves. If you talk about waves basically are, suppose you drop a particle, okay, into the pond, and what will happen, the waves will generate. Okay, so the waves will generate outward. So it will be like this. Okay, there will be some source and there will be these waves getting generated. If you see it from the sides, then you will see that there is some wave pattern, correct? This is your wave pattern. Now the distance, this is known as the crest. This is known as the crest. Okay. And this is known as the trough, correct? These are the troughs. Okay, these are troughs. So if you talk about basically the distance between two consecutive crests or two consecutive troughs, then it is known as the wavelength. This is your wavelength. Okay. And whatever is the speed of this wave, that speed is given by, speed of the wave is given by distance over time taken. Okay, so that lambda covered in one time period, that is 1t. So lambda over t is the speed of the wave. There is one more term that is known as wave number. Wave number, that is denoted by k, and that is given by 2 pi by lambda. Okay, so this is basically your wave number. And there is one more thing, that is your period. Period is your time t. Okay, and this is basically your time in which it completes one cycle completion time. Okay, completion time. Then you have got one more term that is known as amplitude. Amplitude is the vertical displacement, maximum displacement from the mean position. This is your amplitude. Okay, this is your amplitude. This is your amplitude. Okay, so this is a amplitude. One more thing is there, that is known as the frequency. So frequency is defined as the number of cycles per unit time taken. Okay, frequency is basically number of cycles divided by the time taken. So if you talk about it, it will have one cycle covered in t time period. So it is 1 over t. That is your frequency. Correct? So this is the part that you should know for the waves. The general equation for a wave is given by y is equals to a sine kx minus omega t plus phi. Okay, where phi is basically the vertical displacement. Okay, vertical displacement. A is your amplitude, k is your wave number, omega is your angular frequency. Angular frequency is given by 2 pi f. Okay, and frequency is basically given as 2 pi f, and then you have phi is the phase. Okay, remember one thing, all the particles that is doing motion over here, they can be moving vertically up and down like this. Okay, so the oscillations are perpendicular and the wave is traveling rightward. This is known as the transverse wave. Okay, one more type of wave is there, that is known as the longitudinal wave, where the particles oscillate into the direction of the traveling of the energy disturbance. Okay, so if the energy is traveling towards right, then the particles will also be disturbed like this. So this is known as the longitudinal vibrations. Okay, no longitudinal waves. Clear with this? An important next thing is that this is your y. Okay, y is equal to a sine kx minus omega t plus y. One more term is there, that is known as the so this is understood. Okay, this is your wave. If you talk about two waves, and if they are having phase difference of 0, means both of them are having the same phase. Okay, like this. So what will happen? So both of them are adding up at the same interval. So if this happens, this is known as the constructive interference. Okay, this basically is a topic under superposition of waves. Okay, constructive interference. And if they are having the opposite direction, then what will happen? It will be like this. Clear with this part? So this in this case, it would be destructive interference. Okay. So this is the thing. Okay, in the constructive interference, delta phi is given by 2n pi, and in this case, this is given by delta phi can be 2 or 2n pi plus minus some phase difference is there, so you will have pi by 2. Okay, so what will happen if you talk about, let's say, delta x? Okay, so basically remember one equation, delta phi is given by 2 pi by lambda into delta x. This is an important term. Okay, so if it's a delta x is equals to 2n pi, then how much delta phi is basically 2n pi, you will get delta x is equals to n lambda. And if you talk about this, then it will be delta x is equals to 2n plus 1 lambda over 2. I'm taking n is equals to 0, 1, 2, 3, and so on. Okay. So this is the condition. Similarly, 0, 1, 2 over here. So remember, this is your constructive interference and destructive interference. Okay. And the waves. With this part. And remember one thing, if you have a wave that is going from left to right, okay, like this, and if you have a reflection from any wall, then what will happen? It will create nodes and antinodes. Okay, and there will be a formation of the stationary waves, or we call it as the standing waves. Okay, standing waves. Okay. So in the case of standing waves, there are some points which are never into any displacement, that are called as nodes. And similarly, some points are always there which are having some maximum displacement from the mean position, that are known as antinodes. Clear with this part? Yeah. This is your antinode. Yeah, clear with that. This is your antinode. Okay. So, and remember that the distance between the node and node is always lambda by 2, while the distance between node and antinode is always lambda by 4. Okay. So this is the part that you should. Okay. So this is the waves. Okay. Yeah. If you talk about, there is an important experiment in the superposition of the waves, that is given as superposition of the waves, that is what? Yeah, YDSE experiment, Young's double slit experiment for the light waves. So if you have two slits, okay, like this, and their waves are coming, okay, the source will become coherent, means both of the slit will behave in the similar manner. Now if you have got this, this is the surface, okay, this is your screen, then what will happen? There will be some interference at this point. Okay, some interference at this point, and there will be some bright fringes and dark fringes, alternate bright and dark fringes that will be formed onto the screen. Okay, and there is a central bright fringe over here, and there is your dark fringes, then bright fringes, then dark fringes, and so on. Similarly, it goes on the other side as well. Dark fringes, bright fringes, dark fringes, bright fringes. This is the concept. And one more thing is important, that superposition of the waves. Okay, in the superposition of the waves, whenever you are taking the YDSE experiment, your width, okay, your width of fringe width is given as lambda d over small d, where lambda is the wavelength of the light which you are sending, d is the capital distance. This capital D is the distance between the slits and the screen, and small d is the distance between the slits. That is small d. Now remember one more thing, that is if you talk about the waves, okay, superposition of the waves. For one thing, this is your fringe width, okay, and one more thing is there, that is your y distance, okay. So if you talk about, let's say this is your angle, okay, this is your theta, clear? Suppose this is your theta. I will say that y is this, okay. So if I talk about this, that part difference that is created between the two is given as d sine theta, and sine theta is almost equals to tan theta, and that is given by y by d. You can see over here as well, because this is your vertical distance, this is your d, okay. So y over d. So I will get delta x is equals to dy by d. Now if it's a constructive interference, then you already know that delta x is equals to n lambda, that is your bright fringe, okay. And if it's a destructive interference, then you already know delta x is equals to 2n plus 1 lambda over 2, that is your dark fringe. Getting this? So these are the two things over here, okay, and you define the constructive and destructive interference, and you define the distances between them as well. Okay, you can also define the location of the dark and the bright fringes from that. Okay, just compare this value, and remember one more relation, that is delta phi is equals to 2 pi by lambda into delta x. So this is the part for the delta phi. Clear? One more thing is there, diffraction. Diffraction, you can consider lot of openings are there. From that, the light waves will go and interfere. In the ES level, it is not in very depth. Okay, there is one important theorem for this Bragg's diffraction law. Okay, X-ray Bragg's diffraction law, where you want to find out the distances between that interatoms. So basically, what this relation says, delta x is given by that is n lambda, and that is equals to n lambda is equals to 2d sine theta. That is this formula used. Okay, so this is the thing, and one more thing is there, that is known as the polarization of the waves. I will let us talk about this polarization as well. So polarization, I told you, in the polarization of the waves, basically what happens, there is one law that is known as Malus law, which is followed. Suppose there is a light that is going, unpolarized light, okay, and it goes to a slit, and this is some angle, then what will happen, the intensity will decrease. So whatever the intensity of the polarized light would be there, that would be given by the Malus law. And what does the Malus law say? Malus law say that you have got I, that the intensity of the polarized light, that is equals to I naught cos square theta. Okay, so basically this is your Malus law. One more law is there, that is your reflection cases. So what happens in the reflection and the refraction cases? So what happens is, if your light is there and it retracts, okay, like this, and there is some refraction, if the angle between the two is 90 degree, then what will happen, this will be polarized light. Okay, polarized light. This you should also remember. Okay, so this is This is also one of the important laws in polarization. Okay, remember these concepts. Yes. Now the next thing is, next chapter is basically your electricity and DC circuits. Okay. Now if you talk about electricity and DC circuits, electricity and DC circuits, basically you start with something known as potential difference. That potential difference is applied when you apply some positive potential over here, negative potential over here, there will be some potential difference, and due to that the electrons will drift in the opposite direction, and we have got one quantity that is known as drift velocity, and drift velocity is given by Vd. Vd is given by I by NEA. This is given by I by NEA, where I is the current passing through the circuit and N is the number density. N is the number density. E is the electronic charge. Okay, number density. Is the electronic charge that is given by minus 1.6 into 10 to the minus 19 coulomb, but we don't take the minus sign. E is the cross section area, and I is the current through the circuit. Okay. So this is the part for this. Similarly, if you talk about there is drift velocity also calculated on the basis of relaxation time, and it is given by EE by M into tau, where tau is your relaxation time. That is the time required for one particle or one electron to hit the another electron while in motion. E is the electric field. Okay, electric field applied, and M is the mass of that particle. Correct? M is the mass of the particle. That is your electron. And Vd is your drift velocity. There is one more important term that is known as resistivity, and resistivity is given by M upon Ne squared tau. We have already derived this one in the class, so this you need to remember. That M is the mass of the particle, and density, E is the electronic charge, and tau is the relaxation time. And one more thing is there, that is known as current density. Okay, current density, that is sigma. So this is your current, sorry, J. J is the current density. So current density is given by I per unit area. Okay, and I know that this J is equals to sigma times E, where sigma is your conductivity, that is 1 over resistivity. Okay, 1 over resistivity. Okay, this you need to remember. Okay, E is your electric field, J is the current density. So these relations, once you use all of them, then you come up to the definition of resistance, and that resistance is basically given by R, and this is basically given by rho L over A. Okay, where A is the cross section area and L is the length. So suppose you double any wire by stretching, what will happen? The length will get doubled. Okay, area will get half. Okay, area will get half. Okay, clear with this part? So length will get doubled, and area will become half. Okay. Then you can find out the new resistance R dash, that is equals to rho into 2L over A over 2. So it will be 4 times of R. Okay, so such type of problems are necessarily asked in the exam, so you can take account for that. Okay, now we have got Ohm's law. What is Ohm's law? Ohm's law is basically given by V equals to I. Okay, V is equals to IR. Basically, it tells that if you draw the current in the circuit and the voltage, and you increase them linearly, then what will happen? It will be a linear curve, and this is followed as Ohm's law. If you talk about resistance, resistance varies as the temperature as well. That is given by R is equals to R naught 1 plus alpha delta T. where alpha is known as the coefficient of thermal expansion. Okay, coefficient of thermal expansion. Understood this part?
Okay.
So these things you should know for the electricity part. Okay. And power is given by VI, and it is also given as V square by R or I square R. So this relation you should use when voltage is constant across the parallel condition, and this relation I square R you should use when your current is constant in the circuit, mainly the series circuit. Clear? So this is the part that you should know. Okay.
Okay.
Now we'll go to the DC circuits. DC circuits. Okay. So if you talk about DC circuits, basically in order to solve the circuits, basically we have got two types of laws. That is KCL, that is Kirchhoff's current law. One is KVL, that is Kirchhoff's voltage law. KCL states that whatever the current is entering into the junction, that should exit out of the junction. Okay. So this I1 plus I2 plus I3 must be equals to I4 plus I5 plus I6. Okay. So I1 plus I2 plus I3 must be equals to what? I4 plus I5 plus I6. Okay. KVL states that in a loop, the potential drop must be zero. So delta V must be zero. So what does it states? Basically, if you have, let's say, this circuit like this, okay, this is your resistor, okay, then what you should write, let's say this is plus V and the current is flowing in this direction, or let's say always try to take from the positive side of the battery. Then what should I write? Plus V minus I into capital R minus a small r, okay, equal to 0.
Yeah.
So this type of law we should write in the KVL and the KCL. Okay. So this is used in various circuits. We have got one more thing that is known as the potentiometer circuits. Okay. So in the potentiometer, what happens? Suppose you have got, this is the main circuit. Okay. This is your main circuit. You will apply either the EMF and the resistor, and then you have a galvanometer, and this is placed with the jockey over here. So this is your balancing length when there is no current through this branch. So when the current in this branch is equal to 0, this is your balancing length. Suppose you similarly do it for epsilon 2 and you will get, let's say, L2. Then you can compare the two EMFs, and this comparing of EMF is giving you comparing EMF. What you will get? You will get E1 over E2 is equals to L1 by L2. Okay. And the second thing is finding the internal resistance. So finding the internal resistance. So internal resistance is given as finding the internal resistance. So that is internal resistance is small r. Suppose you want to find the internal resistance is small r, that is given by capital R into L1. That is the initial balancing length divided by L2 minus 1. Okay, where L2 is with resistor. So basically what we do is we make a circuit like this. Okay, and this is your wire. Okay, then what I do is, this is your EMF1. Okay, and then what you put is, this is your resistor and this is your galvanometer, and this is your jockey. Okay, then what will happen? You will place a resistor over here. This is your capital R, and then you will solve. And this is your L2, so you will solve accordingly. Okay, so you can find out the unknown resistances as well. Okay, smaller. Hope that is okay. Okay. So these are the things that you should know. Yeah. Okay, and rest of the things, voltage dividers, these you can solve based on the basic concepts. So on the division rule. And remember one thing, that if it is a series circuit, what will happen? R1 plus R2 would be the R equivalent. Okay, R1 plus R2. Similarly, if you want to calculate, let's say, power. Okay, so power is given by I square R1 plus R2. Correct. Similarly, if it is a parallel condition, this is your resistor, second resistor, R1 and R2. Then what will happen? If you connect a V voltage, then you will have R equivalent as so 1 over R equivalent is 1 over R1 plus 1 over R2 and so on. So you will get what power is equals to V square by R1 plus R2. Okay.
Yeah.
R equal to V square by R1 or V square by R2. Okay. So there will be different powers. You can add both of them. You can add both of them to get the final power. Okay. Now one last chapter is there, that is your modern physics. Okay. Modern physics basically your particle physics. Okay. Can you see the slide over here? Hello? Yeah, you can see over here in the plum pudding model that is given by James Thomson. It says that you have a positively charged system, okay, around which the electrons are there, okay, and they are basically neutral in size. So what happens, the positive and the negatively charged balances each other, and you have got a plum pudding model like this. Okay, you remember that? And then we discussed about the Rutherford's gold foil experiment. In this, what he did, basically the radioactive substance emerges the alpha particles. Okay, this alpha particles hits the gold foil, and some of the particles go straight, some particles got deflected, and some particles got what? Deflected 100 degree, 180 degree, correct? So most alpha particles travel through the foil and deflected. From this, we understood that most of the space inside the atom is free up, and there is nothing else. Okay, and some of the region is that which is having a nucleus. So basically, that the particle gets retracted. And if you talk about some other particles, these are your electrons that are very fine in size and very small in size. Okay, and then you have got the orbits in which the electrons move. This is your nucleus, and nucleus is your heavy mass inside the atom, correct? So most alpha particles travel through the foil and deflected. Some alpha particles deflected by small angles, and occasionally the alpha particles travel back from the foil. So this experiment told you about the structure of an atom. Okay. Then we saw the alpha decay, beta decay, and gamma decay. You remember that? So you can see over here, this is Z. Z is your proton number, isn't it? So this is your proton number as well as the atomic number. A is the mass number. And if you talk from X to X dash, there will be an alpha particle that will decay out. Okay. And you will get X dash is equals to Z. So it is having Z minus 2 and A minus 4. So this is the equation for the alpha decay, very important. Okay, we have solved problem based on that. Then the beta decay. Beta decay is basically from Z XA, you can see over here, and you will get X dash. That is your negative beta decay. So minus 1 would be over here. So I have to balance it to get Z plus 1 over here. Similarly, you can have gamma decay, and there is nothing, no particle emission, it's just the rays that are coming out. So you can see over here gamma rays. Okay, remember one more thing, if you talk about alpha is having less penetrating power because it's a very low speed. Similarly, beta has more penetrating power. Similarly, if you talk about gamma has highest penetrating power, even through perspex and paper it will pass through. Okay, and if you talk about this carbon 14, so this carbon 14, if it decays by beta minus decay, what it will form? It will form nitrogen 14. Okay, and this would be your antineutrino, and this is your electron. Correct. Similarly, for the carbon 10 will decay into boron 10, and this will be your neutrino particle, and there will be a positron over here. Okay, you remember this? So you can see over here when it's a beta minus decay. So beta minus decay, you have a anti-neutrino over here, and then an electron coming out. So what happens? Suppose this is your 6 proton, 8 neutron case. It will decay to 7 proton, 7 neutron. Correct. If you talk about beta plus decay, what will happen? This carbon 14 will decay into boron 10. So you can see over here. So in the boron 10, what will happen? It will have from 6 protons, it will come down to 5 protons, while from 4 neutrons, it will come up to 5 neutrons. And this is your neutrino, and this is your positron. Remember the particles, okay? So in the beta minus, electron will emit. In the beta positive, positron will emit. Okay. In the beta minus, anti-neutrino will be out, while in the case of beta plus, there will be neutrino. And since there is a positron coming out positive side, so what will happen? It will go from 6 protons to 5 protons, because one is already out. Correct? In this case, what will happen? It will increase by 1, because there is an electron coming out. Okay. So you can also write these equations and solve. I told you about the binding energy. So what happens? The smaller nucleus are less stable. So they fuse in order to form the bigger compounds, which are having higher binding energy per nucleon. Okay, you can see the graph of binding energy. Similarly, the smaller binding energy based heavier nuclei diffuses into the smaller nuclei to come in a region where there is stability. Okay, and this is your fission and fusion conditions. Okay, so what happens in the fusion? Basically, the deuterium and tritium, let's say, they both combine, and they release a lot of energy, and this helium is formed and neutron is formed. So this is your fusion. Okay, that is going inside the sun. But if you talk about the neutron, if neutron hits a nucleoactive particle, then what will happen? It will emit the neutron. Okay, and like this, and similarly a neutron, and like this. Okay, so there will be bombardment, and due to the bombardment, there will be compounds that will form in the fission reaction. Clear? And then you have got quarks. In the quarks, you can have positive and negative charges, but they can have the subatomic particles which are partial in level. So these leptons are present outside the nucleus, while the hadrons are present inside the nucleus. In the leptons, we discussed about electron, tau, electron, neutrino, tau, neutrino, muon, muon, neutrino. Okay, so basically the large hadron collider that I showed you in the class, who detected the subatomic particles. And if you talk about the hadrons, these hadrons consist of mesons and baryons. In the mesons, you have quark and antiquark. So you have quark and antiquark. Similarly, in the baryons, you have got the protons and the neutrons. And these quarks can be up, down, top, bottom, charm, and string. You can remember their partial fractions to solve the problems. Okay. So these were the topics. I think we have discussed all of these topics. Okay, which are important for the exam. Okay, just revise all of them and try to solve more problems. Is helpful for you, just let me know how do you feel about the video in the comment box, and do let me know if you want any improvements or any topics which you want me to discuss in detail. This was a brief video so that you can solve the problems and get a glimpse through all the topics which are under ES level part 1. Okay, thanks for watching. Bye bye, take care.